All right, so bottom of page A6, absolute value. Bottom of page A6, absolute value. All right, the best definition that we have for absolute value is that it is the distance that you are away from zero. So, for the longest time we've known that if you take the absolute value of 3, you get 3, and if you take the absolute value of -3, you get 3. But in calculus, our goal is to try to understand the reasonings behind things and why they work the way that they do. So if we think of absolute value as the distance away from 0, if you go down the number line to +3, you are 3 units away from 0, right? But if you go down the number line to -3, you're still 3 units away from 0. If you found the distance between -3 and the origin, it would be 3. So if absolute value is the distance away from 0, that's why when you take the absolute value of a negative number, you get a positive number. So here's how we could define absolute value. We're actually going to have to define absolute value using a piecewise defined function. Now remember piecewise, it's basically a function that's defined in pieces, right? So piecewise defined functions. So here's how we can define absolute value. If what's inside your absolute value is greater than or equal to 0, meaning it's positive or equal to 0, you're going to get exactly what you started with. So like the absolute value of 3 was 3. But if what's inside your absolute value is less than 0, meaning it's negative, like the -3, you're going to get the opposite of what you started with. So if what you have in your absolute value is a variable, you are going to have to redefine that function in 2 separate pieces because you don't know whether that variable is positive or negative. So you have to make concessions for each. In the middle of page A7, they tell us that the square root of a squared equals a is not always true. That's only true when a is greater than or equal to 0. What is a true statement is that the square root of a squared is not just equal to a, it's equal to the absolute value of a. Go back to Algebra 1 for a second. You know how in Algebra 1 when you first started solving radical equations, and if you had x squared is equal to 9 and you were trying to get rid of the square, you were told to insert the radical to insert the square root, right? So they would say insert a square root on both sides and don't forget to put in your plus or minus. Didn't that not seem bizarre the first time we heard that? Like, why do I randomly, out of the clear blue sky, throw in a plus or minus into this problem? Well, now it makes a whole lot more sense to us because if by definition the square root of a squared is not a, it's the absolute value of a, then when I took this square root of x squared up here, I would get the absolute value of x. And now we're back to the story we had just a second ago where if I take the absolute value of what, would I get 3? We saw that I could take the absolute value of 3 or -3 and get 3, so that's why over here this x could be either +3 or -3. That's why I have to put that plus or minus in because of that absolute value. So again, we start to explore some of the reasons behind things and getting a deeper definition of concepts that we've worked with before. Okay, so what's that going to flesh out as problems for us? Well, let's look at this first one right here. We've got the absolute value of the square root of 2 minus 1. We're not throwing that into our calculator and getting a decimal. In AP Calculus, you want to give the exact answer unless you're told to give a decimal approximation. On the free response questions on the AP exam, if you give a decimal where you're not supposed to, they'll take a point off. I may only get 2 points for this whole section of this problem I'm working out, and if I get down to the very bottom and I don't write the answer the way that they wanted, I lose one of those 2 points. We can't give away points like that. So all year long, we want to practice giving the exact answer unless we're told to give a decimal approximation. So if I have the absolute value of the square root of 2 minus 1, here's what I have to do. I have to figure out which of these 2 scenarios I'm looking at. Is what's inside my absolute value greater than or equal to 0, or is it less than 0? So what is this? Is it positive or negative? Positive, right, because square root of 2 is bigger than 1, right? Square root of 1 is 1, so square root of 2 would have to be bigger than that. So if I had something larger than 1 minus 1, that would leave me a positive value. So if what's inside your absolute value is positive, then what do you get? Yeah, it's the square root of 2 minus 1, the exact same thing you started with. All right, look at the next one. This is like homework problem number 5. We've got the absolute value of 3 minus pi. I'm not throwing that into my calculator. I know that pi is 3.14, so is what's inside my absolute value, is it positive or negative? Negative. So when I take the absolute value of a negative number, what do I get? Right, the opposite of what I started with. So I would get the opposite of 3 minus pi. So the opposite of 3 minus pi would be a negative 3 and a positive pi. They're always going to write the positive first and the negative second, but you could say negative 3 plus pi or pi minus 3. All right, example 5, they ask me to take the absolute value of 3x minus 2 and to write it without using the absolute value symbol. Basically, they're asking me to redefine this function as a piecewise, like we were mentioning before. So I'm going to have to think about, okay, what if what's inside my absolute value is greater than or equal to 0? And what if what's inside my absolute value is less than 0? Because again, that was the same definition that we talked through over here, right? That's how we could define it in the two pieces. So if what's inside my absolute value is greater than or equal to 0, what am I going to get? 3x minus 2, right, exactly what I started with. But if what's inside my absolute value is less than 0, what am I going to get? Yep, the opposite of that, a positive 2 and a negative 3x, so 2 minus 3x. So I have redefined that function without the absolute value. Now, let's simplify that a little bit. When you typically see a piecewise defined function, you don't have an equation over here to solve, right? I mean, normally it says if x is greater than 2, use this piece. If x is less than or equal to 2, use this piece, or something like that, right? There's just like a normal number over here. So let's simplify this a little bit, and let's tell our reader, instead of 3x minus 2 having to be greater than or equal to 0, let's tell it what x needs to be. So all I'd have to do is come over here and say, okay, if 3x minus 2 needs to be greater than or equal to 0, just solve that for x. So add 2 to both sides and divide by 3. And that'll tell you what x needs to be. And so then I can replace the equation with just the single value of x, and that makes it a lot easier to read. So that's going to be like homework problem number 9. That's how I can express an absolute value as a piecewise defined function and get rid of my absolute value. Okay, so on the top of the page here, we've basically already discovered the rule for an absolute value equality, but they tell me that if you have an absolute value equal to a number, the way you'll solve that absolute value equation is that you'll take what's inside the absolute value and set it equal to a positive and a negative of what's on the other side. So again, you could kind of think of this, if this was the absolute value of x is equal to 3. A little higher up on the page, we already saw that that could be a positive 3 or a negative 3 in the place of x. So our answer would be x could be positive or negative 3. I would get that same thing if I took what was inside the absolute value and set it equal to a positive and a negative of what's on the other side. So let's look at example number 6. Just a reminder up here with this guy in your notes that every absolute value function is going to be a piecewise defined function. All right, so let's take what we had in our absolute value here and set it equal to both a positive and a negative of what's on the other side. So we'll have 2x minus 5 is equal to both a positive and a negative 3. So I'm going to write that as two separate equations. 2x minus 5 equals 3 and 2x minus 5 equals negative 3. All right, so let's solve this first one. What are you going to do to solve the first one? Perfect. Add 5, divide by 2. And then same story with the second one, right? We saw last year that with this type of problem, we do need to check for extraneous roots. So you don't have to write it out on your paper. You can just spot check it quickly in your head to go through and say, okay, 2 times 4 is 8 minus 5, absolute value of that. So I'd get absolute value of 3 is 3. And if I plug the 1 in, 2 times 1 is 2, minus 5 is negative 3, absolute value of negative 3 is 3. So both of those do work. I don't have an extraneous root. All right, let's talk about our absolute value inequalities. Absolute value inequalities. Now, there are rules for our absolute value inequalities. I just can't remember them to save my life. So you know me, I always have to have some type of mnemonic device to remember everything because I can't keep it straight. I'm forever like putting a, greater than where I'm supposed to have a less than, or a positive where I'm supposed to have a negative, or an and where I'm supposed to have an or something along those lines. So I mentioned to you last year that a friend of mine that was an engineer had given me a really simple way that you could work every single absolute value inequality that you ever see. It basically creates those formulas for you. So what we did last year was we first had to figure out whether what we were working with was a conjunction or a disjunction. So see how this one kind of looks like a C when I have a less than symbol? That's a conjunction. That's an and statement. And this guy over here, if I draw a bar straight up and down right there, it makes that one look like a capital D. So that would be a disjunction. Now, if you want to use that little shortcut for determining if it's a conjunction or a disjunction, the only thing that you have to be careful of is you can write inequalities a couple of different ways. Like the absolute value of x is less than 2. That's the same thing as if I turn it around this way, right? Little n towards the x, big N towards the 2, little n towards the x, big N towards the 2. That's an equivalent statement. X, absolute value of x is less than 2, or 2 is greater than the absolute value of x. But here, it looks like a conjunction, and here, it looks like a disjunction. So if you want to use that little CD shortcut thing, it only works when x is on the left-hand side. So you would need to rewrite it that way first if you wanted to look at it to see if it was a conjunction or disjunction. So just be careful of that. Okay, so this first guy right here, what does that look like? Example 7, does that look like a conjunction or a disjunction? Conjunction, yeah, it looks like one of those C's. So if that's a conjunction, here was the shortcut that we used last year. We said copy exactly what you had before or without the absolute value. So we would copy x minus 5 is less than 2 without the absolute value. Then copy the same sign on the other side. So we had less than, copy that same sign, and copy the opposite of your number. I had a positive 2, so I'm going to use a negative 2. So again, copy exactly what you had without the absolute value, copy the same sign, copy the opposite number. Great. How is that any easier to remember than the formula? Well, I get to do the same thing on all of them. Conjunctions, disjunctions, I get to do them all the same way instead of having to do them 2 separate ways. Okay? So now let's finish solving this. We know this is a conjunction, so it's an and statement, so I can leave it together. So how do I finish solving that to get x by itself? Add 5, right? So we'll add 5 all the way across, and we'll have 3 is less than x is less than 7, and we'll give that answer in interval notation. All right, example 8, is that a conjunction or a disjunction? Disjunction, because it looks like a D. So for this one, again, use that same little shortcut. Oh, let me back up one thing on example 7. I mentioned to you yesterday that you could do these inequalities on your calculator. So I just wanted to show you, if you went to y equals and you threw this inequality in, absolute value of x minus 5 is less than 2, the answer that we just got was the area between 3 and 7, and sure enough, that's what my calculator is going to give me. It's going to give me that region between 3 and 7. So it would be a quick way to spot check myself if I had a chance to do that. Don't have to, but if you wanted to, you definitely could. So again, for this guy, we're going to use our little shortcut. We're going to copy exactly what we had without the absolute value, copy that same sign over on the other side, and copy the opposite of that number. So copy exactly what we have, same sign, opposite number. Now, you've already told me that this one is a disjunction, so here's the only thing I have to keep straight. I get to do the same thing every single time, no matter what type of inequality it is. I just have to remember whether to put an and in or put an or in. And you don't have to write and in. You can just leave the whole thing put together. But if it's an or statement, you do have to break it apart and put or in. So since this is a disjunction, I do need to break those two pieces apart and put or in. That's the only extra thing that I have to do. Okay, so let's start with the inequality on the left over here. How am I going to get x by itself? Perfect. Subtract 2, divide by 3. And same thing on the other side. Subtract 2, divide by 3. Now, when I do a disjunction, I'm literally going to get two completely separate pieces, like two completely different answers, but both of them are my answer. And we don't want to confuse the reader with saying, okay, it's this one and this one. Wait, this was a disjunction. Maybe I'm supposed to write it was this one or this one. It starts getting confusing. All you have to do is when you write your solution in your interval notation, we're going to put the little union symbol in between our two answers. So basically we're saying the answer is negative infinity to negative 2 united with 2/3 to infinity. And you'll see them do that in our textbook, and they do it that way on the AP exam as well. So they use the little union symbol to join together the pieces of our solution. Okay, so that finishes off Appendix A, the review of our equations and inequalities. So we want to get a little bit of a jump start today on Appendix B. We'll be working on that lesson next. And so we're going to go ahead and work a little bit on Appendix B today, and then we'll pick up with it again. On Appendix B, we get to learn what an x-axis is. All right, page A10 for Appendix B, page A10. On A10, we start off with some bold print terms. We've got x-coordinate, y-coordinate, rectangular coordinate system, Cartesian coordinate system, coordinate plane, Cartesian plane, coordinate axes. I mean, all of those are terms that we're very familiar with. But to summarize that and kind of give the brief version, the rectangular coordinate system is the typical XY axis that we work with in 2 dimensions. It's named the Cartesian plane after the French mathematician René Descartes, because he was the one that kind of put all the ideas together, so we name it Cartesian after him. It is basically a horizontal axis that we call the x-axis, a vertical axis that we call the y-axis. They intersect at the origin. You understand why they call it a rectangular coordinate system because you've worked with polar coordinates, so you understand where to plot a point here, I would maybe go over and up and make a rectangular region. When I graph polar coordinates on concentric circles, it's not rectangular, it's circular. So that's also where it gets its name for the rectangular coordinate system. Those axes split the Cartesian plane into 4 equal pieces. We call them quadrants. We number them with Roman numerals counterclockwise, so 1, 2, 3, 4. And we could plot a point in that Cartesian plane. We usually call it an ordered pair because it's a pair of numbers and the order matters. So x comes first, y comes second, and it's in alphabetical order, so it's easy to remember. What is new to us is the name for the x-coordinate and the y-coordinate. I gave these to you last year, but they weren't in our book last year. So this year they are in our book, and they'll utilize them. The name of the x-coordinate is the abscissa, and the name of the y-coordinate is the ordinate. So all of those bold print terms there on pages A10 and A11 that we want to pay particular attention to because we usually have bold print terms on our quizzes in the multiple choice. Okay, look at example 1. Example number 1, it says, describe and sketch the regions given by the following sets. The set xy such that x is greater than or equal to 0. Okay, why are they using that crazy set builder notation? Here's why. If they just told me to graph x is greater than or equal to 0, I don't know what they want me to do. I don't know if they just want me to do a number line where I would come over here and say, okay, here's 0, so let me put a bracket at 0 and let me shade all the values greater than that? Or are they actually wanting me to do like an XY axis and go through and say, okay, here's where X is equal to 0 and all the values greater than that are over here? How am I supposed to know what they want me to do? That is why we use set builder notation, because then I'll know what they're looking for. When this says the set XY such that X is greater than or equal to 0, yesterday they didn't have that, right? In the one we did yesterday, it just said the set X such that. So if it said the set X such that, I would know they wanted this. Because it says the set XY such that X is greater than or equal to 0, then I know they're looking for two-dimensional. So remember that when we are graphing inequalities in 2 dimensions, we start graphing it just as if that said equal to. So if this said X equals 0, then I would just have a vertical line at 0, right? If it's greater than equal to or less than equal to, I'll use a solid line. If it's just greater than or less than, All right, so this was greater than equal to, so that's why we use the solid line. All right, then we need to figure out which side to shade. When you draw your line in the XY axis, it divides that Cartesian plane into 2 half planes. One complete half plane is your solution, and one complete half plane is not your solution. Sometimes, like in this case, yeah, we can use common sense and go, I know where the numbers greater than or equal to 0 are, so that's the half plane that I'm going to shade. But other times I may not know, and that's where we can pick a test point, because if you choose one point and you plug it back into that inequality and it makes a true statement, then that lets you know every point on that side would work. If you plug it back in and it doesn't work, it doesn't give you a true statement, then you know no point on that side would work and that you need to shade the other side. All right, so look at the next one. For the next one, we've got the set XY such that Y is equal to 1. So not an inequality here, an equality, but still in 2 dimensions instead of 1. So what does Y equals 1 look like? Yeah, horizontal line at 1. By the way, if you have trouble remembering if it's horizontal or vertical, remember that if it's Y equals 1, at some point it has to cross the y-axis and be equal to 1, right? So if it's y equals something, it crosses over the y-axis. That makes it horizontal. If it's x equals something, it's got to cross over the x-axis. That makes it vertical. I think that's hard for us to keep straight just because we tend to associate the horizontal axis, x-axis, so when it's a horizontal line, we think it ought to be x equals something instead of y equals something. I think that's why that's hard for us to maintain. All right, look at the next one. The next one, we've got the set xy such that the absolute value of y is less than 1. All right, I need to come over here and figure out what the absolute value of y is less than 1 equals so that then I know how to go back and graph whatever that is, okay? So is this a conjunction or a disjunction? Conjunction, because that looks like a C, so it's going to be an and statement. So I'm going to copy exactly what I have, copy the same sign on the other side, copy the opposite number, and I'm going to leave it all together as one piece as a conjunction. Okay, so now I want to graph -1 is less than y is less than 1. I graph an inequality just like I would an equality. So first start and think of it as if those were equal signs right there. If you graphed y equals 1 and y equals -1, what would that look like? Horizontal lines, vertical lines? Horizontal lines, right. Are they going to be dotted or solid? Dotted, because it was just less than, it wasn't less than equal to, right? Now this is another one of those that we can use common sense and figure out where to shade, but that might not always be the case. So if I had something that was more complicated, that was a little harder for me to figure out, I could rewrite this as 2 separate inequalities. We already know it's a conjunction, so I would have the and in between. So I could go through and I could first say, okay, what does y is greater than -1 look like? Well, the values greater than -1 come this way, so I would shade up here. And then I could go through and say, okay, what does y is less than 1 look like? Well, those would be the values less than 1. I would shade down here. And remember that with a system of inequalities, solution equals intersection. Where those two overlap is my final solution. So the only place that I have crosshairs is in this region right here, so that would be my solution. Now, for this one, most likely you could have just looked at that and automatically known, okay, what was between 1 and -1 was that little piece, and that's fine. Remember, there's no way to write this answer that your shaded graph is your solution. It is your final answer. Okay? All right, then last things that we want to finish up with today are distance and slope. So they give us both of those formulas here. We've got our distance formula and our slope formula. What does the distance formula come from? Anybody remember where we get it from? Nice, Pythagorean theorem. All right, distance formula comes from the Pythagorean theorem because you could go through, if you were trying to find the distance between 2 points, you could go through and make a rectangle out of that and say a squared plus b squared is equal to d squared. And so then if I go through and I say I don't really want the distance squared, I just want the plain distance, take the square root of both of those sides, and I can look at this and say, okay, what was A? Oh, well, it was just the change in the x values. What was B? Oh, it was just the change in the y values. So that's where that comes from. We worked a lot with that last year in where the proof of that came from as well, but just wanted to remind you of that. So if I have 2 points, I'm going to call this point number 1 and this point number 2. And so I could label it the x value for point 1 and the y value for point 1, the x value for point 2, and the y value for point 2. So then it's just a matter of straight substitution, right? Where I could say x2 minus x1 and y2 minus y1. So 5 minus 1 would give me 4, and 3 minus a -2 would give me 5. 16 and 25 would give me 41. And again, I'm giving the exact answer, not a decimal approximation. For slope, we have tons of different formulas for slope. Slope just measures the steepness of a line, and we'll spend a lot more time on that in the last half of this lesson. But slope is change in y over change in x, opposite of a over b, y2 minus y1 over x2 minus x1, rise over run, lots of different ways we've defined that. So we're going to use the same values we had a second ago for the change in the y, and the same values we had a second ago for the change in the x, and we'll get our slope of 5/4. Okay? So because we were working part in Appendix A and part in Appendix B today, you'll have problems on 2 separate pages, so just make note of that.